Hi, good afternoon, everyone, and thank you so much for joining us. Welcome to the How Often Should Instruments Be Calibrated webinar. Today, we will be examining how you can determine appropriate calibration intervals and prioritize your instruments to increase efficiency, ensure instrument reliability, quality, and safety as well. I'd like to introduce myself. I'm Katie Turner, the Office of Marketing Coordinator here at Beamex Inc. I will be your host today. We will have a different presenter, Mr. Eric Webb. But what I do for Beamex is I handle the marketing operations for the U.S. and Canadian markets. Today, our presenter will be Mr. Eric Webb. He is a regional account manager at Beamex Inc., and he is actually quite an expert, being a certified metrologist. He has over 20 years of calibration and test equipment experience in sales, service, management, quality, and assurance as well. Today, Eric manages sales and strategic accounts for Beamex in Texas and Oklahoma. Before I hand it over to Eric, I'd like to tell you a little bit about Beamex and who we are and what we do. Beamex was founded over 30 years ago, back in 1975. Our mission has and always will be to manufacture extremely accurate, high-quality calibration equipment and software systems for the process industries. That picture on the right-hand side there is our corporate headquarters, our manufacturing and research and development facility in Pietarsaari, Finland. Our key markets include pharmaceutical, power and energy, oil and gas, petrochemical, chemical, and food and beverage. Today we have over 10,000 customers throughout the world with companies such as Nestle, AstraZeneca, Southern Company, BP, and ConocoPhillips, just to name a couple. Before I hand it over to Eric, I have one more slide to go through, and this is what really differentiates the Beamex offering from other companies. It's the idea of this integrated calibration solution, which is made up of software, portable calibrators, workstations, and professional services. If we start off with calibration software, every plant right now has some sort of system in place for managing their calibrations, whether you're working with temperature or pressure or even multivariable transmitters. You have some sort of system in place to monitor and track your instruments. Today you may be using just pen and paper or spreadsheets, possibly even a database, to determine what instruments require regular calibration to ensure they're performing and measuring to any specified tolerances. Especially with increasing regulations from agencies in the U.S. like the FDA and EPA, having a solid system in place is vital. Calibration software is a tool that you can use to support and guide your calibration activities, provide documentation, and traceability as well. Next, we move over to the portable calibrators. And the portable calibrators are anything from just a standard single function calibrator all the way up to a multifunction or documenting calibrator. We recently introduced the Beamex MC6 Advanced Field Calibrator and Communicator, which is the world's first Profibus communicator. Down in the bottom left-hand corner is the workstations aspect. In some instances, it's much better for an instrument to be removed from the line when brought to a bench to calibrate in a shop. What you see there is the MCS200. It's actually a modular test and calibration system for workshops where a multifunction documenting calibrator is actually panel mounted into the bench. And the final aspect is the professional services, which is hardware and software service support, training, recalibration, and repair services as well. So overall, the combination of all of these, the software, the portable calibrators, the workstations, and the professional services are what form this integrated calibration solution to run your program. So with that, I appreciate you listening to the little spiel about Beamex, and I would like to welcome Mr. Eric Webb to present on how often instruments should be calibrated. Welcome, Eric.
As Katie stated, I have basically been in the calibration business for over 20 years, and what we're going to discuss today is how to establish calibration intervals at your facility for your instruments, and at the same time we're going to show you how the CMS calibration management software history trend module can assist you and help you do the analysis that's required to come up with the right calibration intervals for the instruments that you have. So moving into the first slide here, some trends that have been noticed over the last couple of years with regards to calibration. Technology is becoming more sophisticated and more accurate, and in order to test this equipment, technicians and users must place an emphasis on using good calibration practices. Natural evolution to achieve this is through the use of automation. Increased levels of regulation and risk management practices have led to an increased demand for documentation. Administrative tasks continue to increase this, reducing the amount of time that the technical staff has to perform calibrations and maintenance in the facility. Paperless calibration was developed to meet this specific need. The cost of maintenance continues to be a hot-button issue in this industry. As a result, there's a lot more emphasis being placed on life cycles for instrumentation. Smart transmitters are requiring field communicators, which I'm sure a lot of you have noticed, and the technical demands for the new multivariable transmitters have really stressed the need for multifunction calibrators to help perform that job. So calibration in industrial applications. What we're talking about when it comes to the process of doing this measurement, a lot of it comes back to drift. Drift is a result of age, environmental fluctuation, stress, which can be in the form of vibration, shock, or multiple other factors. Reliability is reduced over time, and without correction can affect production. So drift has the ability to impact every aspect of the process manufacturing. Calibration of these instruments based on proper intervals will minimize this drift and reduce its impact on the production process. Some common misbeliefs, and some of these you may not believe that somebody actually said this, but the reality is that we hear these three topics pretty often, and they all have relevance in what you do because they relate directly back to the end result of your product. So for number one, we don't need to calibrate. In order to achieve the desired result of your manufacturing process, in the end, which is a quality product, you must first know that the process itself is occurring in the way in which it was engineered. Calibration validates this through measurement and comparison of those results. Secondly, we don't need to calibrate field dose instruments because they're digital, and the digital output is always accurate and correct. There have been a lot of improvements in transmitters. Digital field bus signal is indicative of one of those. However, field bus instruments are just as likely to be affected by drift over time as any other instrument. They still require periodic calibration to ensure that they are accurate. Number three, new instruments do not require calibration. New instrument may sit on a shelf for just as an example, for maybe a year before they're sold. They may be handled poorly by a carrier such as UPS or FedEx or however they're delivered. They could have been exposed to any number of environments that could affect their accuracy. Initial inspection through calibration provides proof that the instrument is good before it is allowed into your process. This, in turn, will set a baseline for stability analysis and gets the required instrument information into your calibration maintenance database. So calibration doesn't only serve in this respect to ensure that it's good, but it's also a way of getting all the particular information for that particular asset, be it the manufacturer, model number, serial number, the specific program information, if it is, for example, a field bus device, so that it's already into your system and will be tracked as such from that day forward. When an engineer buys a particular sensor, the instrument manufacturer provides technical specifications, and those include details regarding the maximum drift of that sensor over a given period of time. Through proper documentation, meaning the use of Beamex documented calibrator and CMX calibration management software that has the CMX history trend option installed, that engineer can now verify that the sensor he or she has purchased actually performed within the specified tolerance over a certain time period. If it hasn't, then that engineer now has data that they can present to the manufacturer or vendor that will support their findings, and history trend will allow you to analyze drift over certain periods of time. So when we're talking about the CMX software and how it integrates with the documenting calibrators and such, what we're looking at here on this particular slide, and once your CMX software is installed into your laptop or your standalone computer, you can load all of your instrumentation into it in a database format. Once all that information is in there, you will have specific icons, and when we do the demo here in a few minutes, I'll show you a little bit more about that. But it helps you identify which instruments are due for calibration. And once you've identified an instrument or selected instruments that, say, you want to do for a particular shift, what you would do is select those instruments in CMX, and then in slide 2, you would actually connect your documenting calibrator, which what you're looking at there is the MC6, and you would basically drag and drop the information for those particular instruments that need to be calibrated directly into the MC6. Once they're in there, you can take your MC6 out into the plant and perform these calibrations, and all of the information pertaining to that particular instrument, including the calibration procedure, are stored inside the MC6, at which point you bring up that instrument and bring up the calibration procedure, which shows you directly exactly how to hook up the instrument to the MC6 calibrator. And it shows you step-by-step, takes you through the process of running the calibration. And a lot of calibrations are fully automated, say for a temperature transmitter or something like that. And you would hit the start button, and it will run through the process, record all of the data, and let you know at the end whether or not that particular instrument passed or failed. At which point, if it passed, you could complete your calibrations for the day, come back into the shop, reconnect the MC6 to your computer, and upload all of that data directly back into the CMX software. At that point, it becomes a static record that is updated. It updates that particular tag or position within the system, and it keeps it current until the next time it's due for calibration. If you were to run reports or, as we spoke to, the history trend type of analysis, it will pull all that information automatically from that database record and put it into a context that's going to make it easier for you to perform the analysis that you need to do. So now we're going to talk a little bit about history trend analysis. I know that's kind of an ominous term, but the reality is it's simply a way of comparing data to look at a much broader picture of how that instrument's performing over a given period of time. What history trend analysis does is it allows the end user to look at drift over a specific period, and that can be, say, from the date that particular asset was installed into the system, or you can look at it over a shorter period of time. Say you wanted to look at the last 3 calibration cycles and see how that instrument has performed. There's a lot of flexibility, and when we do the demonstration here in a few minutes, I think it's going to be pretty clear how easy it really is to use. CMX is going to store every calibration event in the database. History trend pulls this data together automatically and puts it at your fingertips for you to look at. History trend allows you to see when a new device is installed and calibrated, and this may be important when you're looking at a particular position that may have had several different model numbers installed over its period of time from when you first started using this software. And when we get a little later into the slideshow presentation, I have a slide that will represent that. I'll speak to it in a little more detail. But from this information, you can determine if a specific model of instrument is better than another for a given position in the process. Another thing the history trend does is it provides information in numerical and graphical form to make the interval analysis for calibration intervals easy to determine. And as I stated, we'll look at that a little further down the road. Some of the benefits of running a history trend analysis are as follows. The information that's provided makes the analysis easy for determining the optimum calibration interval. And you may ask why that's important. Well, given that you have, in some cases, thousands of tags or positions that you have to calibrate annually, if you were able to adjust those calibration intervals based on performance, and over time you were able to eliminate some of those actions that you would normally do, say, every 6 months, you're not only going to save time, it's going to allow you to do other maintenance activities or stay, more current on your existing calibrations. But it's going to save you money in the terms of you're not wasting labor by going out and performing actions that would be considered unnecessary, because that particular instrument has shown a history of being able to maintain its tolerance for a longer period of time than just, say, the 6 months that you would normally calibrate it on as calibration interval. The history trend also will allow you to the comparison of like instruments by different manufacturers to identify the unit that works best or is the most accurate over time. And there's a lot of the different manufacturers of sensors out there, and even one manufacturer may make 4 or 5 different temperature transmitters that would meet the particular criteria for what you're doing. If you could determine that over a period of time, one particular sensor performed well enough that you didn't have to perform calibration actions as often, it might be more financially reasonable to use that particular transmitter when other transmitters based on age or life cycle would need to be replaced. Because once again, it's going to save you time and money down the road, which in this day and age we're all trying to do. There's a time savings involved, and I referenced that a little bit. Doing this manually, and I'm not sure which of you may have done this before, but doing this manually is extremely time consuming. It requires a lot of documentation, and the analysis that you actually have to do in terms of comparing data, it can wind up taking you much longer in terms of the amount of time that you would spend that would somewhat consume the time savings that you would have by using an automated software such as the CMX calibration software with the history trend module. History trend analysis is also going to verify instrument performance compared to the manufacturer specifications. So it's going to look at how did this particular instrument perform as a whole based on the manufacturer's specs. And from that, you can determine whether it's primarily in tolerance, if it's out of tolerance, is that significant. Significant is a term in calibration that defines when an instrument, say, is out of tolerance if by more than 1.5 times what its manufacturer's specified tolerance would be. A significant out of tolerance condition typically is a red flag to an operator or an end user that this instrument has drifted much more than was anticipated during that particular calibration cycle. And typically a review would need to be performed at that point to determine what calibration cycle would need to be put in place in order to keep that instrument in tolerance. A significant event when it comes to calibration has the ability to not only impact production, but it can seriously affect the end product, because the instrument itself was so far out of specifications that the results that were gained through the process may have been well outside the specs that were intended through the engineering process. So when it comes to supplier evaluation, as I stated a few minutes ago, there's many manufacturers and model numbers of sensors out there. The CMX history trend allows the engineer to compare one manufacturer model to another and determine which sensor makes the most sense for a particular position. This can save money and time that can be spent by consuming more frequent calibrations when another particular device would allow you to expand that out. So this kind of really gets to the heart of what our discussion is about today. When calibration frequency can be decreased, meaning when can I adjust the calibration interval to make it a longer period of time between calibrations. If the instrument performs in manufacturer specs over an established calibration interval with little or no drift, and then based on the location, is that instrument in a critical area? Is it in a low priority location? These are things that would have to be determined, either by the individual or your particular regulations that govern that particular process. So the calibration interval may be increased, thus reducing calibration frequency. There's a rule of thumb in calibration that if you can go 3 successive calibration cycles with no out of tolerance conditions reported, that would typically justify an increase of 50% of that calibration interval. And for example, if you have a transmitter that is on a 6-month calibration cycle, meaning it's calibrated every 6 months, and you were to go for 3 successive calibration cycles with little to no drift, and that unit testing and being well inside its tolerance, then that would typically justify an increase of 50%, thus taking that calibration interval from 6 months to 9 months. And then if you were to go 3 more intervals and see the same results, then you could once again increase that calibration interval from, say, 9 months to a year. So that would effectively increase that interval by 100% over a 6-cycle period. Now, on the opposite end of that is when calibration frequency should be increased, meaning a calibration interval for a particular asset would need to be reduced based on analysis of data. So if a particular sensor has drifted outside its tolerance over time, and depending on where that sensor is located, particularly if it's in a critical process area, and that error is significant, meaning it's 1.5 times greater than the specified tolerance that was put forth by the manufacturer. The rule of thumb would tell us that it would be wise to reduce that calibration interval by half. So, for example, if we were once again on a 6-month calibration interval, and we noticed that a particular asset had drifted significantly out of tolerance during that 6-month period, we would want to reduce that cycle to 3 months. And then after that first cycle of 3 months, we would perform some more analysis of that particular asset to determine whether or not there was significant drift over a 3-month period, and to what extent was that drift verified in terms of data. So if it was significant, then we would once again want to reduce that, and more than likely it would go from 3 months to a month. Or at that point, you might want to make the determination that this particular sensor is drifting so much that it might warrant replacement. You might want to evaluate for a different manufacturer or model number for that particular sensor, once again based on if it's in a critical area of the plant or something like of that nature. Because calibration intervals can be any length. They can be governed by days, weeks, months, or even years. In a calibration lab, it's very normal to see there's instruments that are calibrated every day. There are some instruments that are calibrated every month, and then that particular interval analysis is dictated by each particular instrument within the shop. And I know that may sound ominous to some of you that, like I said, have thousands of tags. But when you start looking at this in terms of, say, a particular model number, if you have 200 temperature transmitters within your facility, you can run a history trend analysis that's going to show you the performance of all of those transmitters over a particular period of time. And this can help you to establish a frequency by model number for calibration intervals for just that particular type of device. So it doesn't necessarily have to be on an end units per device type of evaluation. Sometimes industry regulations may give you some guidance when it comes to doing that, but the best rule of thumb is to look at it in a structured basis. Look at it first as I'm going to look at this particular manufacturer and model number of device, and then from that I'm going to evaluate all of those devices to make sure that there aren't a couple in there that are drifting worse than all of the others. And that would help you identify also which ones would need to be replaced on a more frequent basis than the rest. So what we're looking at right now on your right-hand side is an actual history trend analysis that was done by the CMX software. And this utility is really, it's a multitude of data. You can do it either for a position or for a particular device. And by that, a position may have multiple devices over a particular period of time. You can look at all of those together, or you can look at them individually. You can see in the middle section, the data is displayed graphically, and then down at the bottom, it's displayed numerically, so that you can see the trend visually, and then look at the calibration actions individually to determine where the most gross error may have been for a particular device. So the biggest difference between just looking at a calibration certificate, which just gives you the standard results, and the history trend is that you can view multiple calibration results at the same time. So by looking at the graphical overlay of all of the history of that particular device, it really gives you a much broader picture in terms of how it performed. So what we've done here is we've blown up the graphical portion of a history trend analysis. And if you look at the bottom row on any of those three graphs, you're going to see, and the date format is a little different than what most of us would see here in the U.S. But if you look on the very left, it's going to show you, I'll get my pointer there, right there, okay, that the initial calibration for this device was performed on February 19th of 2000. Okay, it was calibrated again in November of 2000, again in July of 2001, et cetera, all the way down through January of 2005. Up in the top left, where that pointer is pointed right now, it shows you gives you the understanding of what each color and line or circle represent. So the green circles represent the maximum error for that device, and the blue line represents the error limit, so in terms of highs and lows. So this blue line and this blue line would be the specified tolerance that the manufacturer provided for that particular instrument. And the green circle and the green line shows whether each calibration interval found it to be in tolerance or out of tolerance, and then the lines connect those to form the graph. So you can see it was in tolerance in its first calibration, and as it followed on, it tended to drift to where, at such a point where it was actually out of tolerance just after the July calibration. And at that point, it was adjusted to be brought back into tolerance. So that's going to be representative of before and after data, with the top line being after data, and then it drifted in the other direction after that. So, and that's very common with particular instruments. If they drift in a particular direction and then are adjusted, a lot of times that drift will reverse itself and go in the other direction. So over time, you can see how a particular instrument is performed and whether or not it would be justifiable to replace that instrument or optimize it. All right. And with this slide, this gives you a little broader understanding. Now it's including the graphical form as well as the numerical form for this particular device. And this is actually a position ID. If you look at the left, it shows you 101 BRPT 0002. Okay, so initially they used a Fisher-Rosemap 3051 to fill the function for this particular device, and it gives you the calibration date, whether the data that's been recorded was as found or as left. Oh, arrow keeps disappearing. So it would basically be rejected or considered a failure if the error was greater than 0.5% of span. So if you look at this very first error, you're reading 0.928, which is almost almost 2 times the specified tolerance, which would be considered significant. So if you look just below that, you see as left data, which shows that it was performed on the same date and with the same rejection error. Once it was adjusted, it met a 0.340% of span, which is well inside the 0.5% that was specified by the manufacturer. So at that point, that asset was considered to be passing. And then if we look a little further down, you see that it passed the next 3 intervals, although if you look at it, the trend is getting worse with each successive calibration. So when it was initially adjusted and left, it was 0.340. The next interval, which was 6 months later, it drifted a little bit more, 0.402. The next interval, which was 6 months after that, it was at 0.465. And then subsequently went out of tolerance again 6 months later at 0.570. So at this point, the end user decided that it was time to replace this instrument. And as you can see here, they replaced that instrument in the same position with an Endress-Hauser PNC 71. Okay, so when it was initially put into service, the initial calibration on it at the same tolerance of 0.5% of span, it was very good, 0.095, which is just shy of 0.1%. So if you look at the history of this particular sensor, over time, yes, there was some drift, but it was very insignificant. It went from 0.085 to 0.15 to 0.195 to 0.188, 0.2, and 0.285. So in terms of drift, that's very minor. And basically, that was over a 3-year period. The unit passed every calibration. So the end user, if you look towards the bottom, actually adjusted that interval to a year versus 6 months in February of 2004. And in March 2005, that unit had very little drift and was still serviceable and very well in tolerance. So in this particular example, this analysis worked both for tracking underperforming instruments in the case of the Fisher-Rose map 3051, and those that overperformed in the same position, meaning the Andrews Hauser, which was his justification for modifying his calibration interval and increasing that interval from 6 months to 12 months, just eliminating the need for calibrating this instrument more than once a year. So by this example, you can see that there was a time savings. They identified through analysis the need for replacement of the Fisher-Rose map device, and they've also identified that the Andrews Hauser, at least in this particular position, has performed very well over an extended period of time. So in the future, it would probably be better to put another Andrews Hauser device in another location in the plant with similar characteristics based on the data that was collected and analyzed through this one history trend analysis. So what we're hoping that you would be able to see through using this would be, if you were to extrapolate that out to look at the entire facility, how many calibrations can you eliminate over the course of the year just by doing a history trend analysis? Or how many underperforming instruments can you identify that are going to reduce the amount of time that it takes to service? Because as you've seen, once you do a calibration and it's out of tolerance, if you have to adjust the device, then you just invested more time in that one particular asset, which keeps you away from doing other maintenance activities. So in the big picture, it can save you a lot on both sides of the page, both in terms of underperforming and overperforming assets. So I hope that you gained some understanding through all of this. And what we're going to move on to now is this next slide is going to kind of point out the areas that I just spoke to. So, like I said, this very first action identified that the initial calibration failed. Okay? It was subsequently adjusted to bring it into a passing performance, as is identified by the second line of the numerical data. And if we go further down, the black line shows that point at which it failed again and was subsequently replaced. So when it was replaced, if you see, based on the two blue lines, the unit that was brought in, when it was calibrated, it was about as close to center as you can get. And that's really what you're looking for, is the mean average of that particular span. If you're in the middle, then you have the benefit, if there is drift, that whether it be higher or lower than nominal, you're going to at least be within tolerance for a specific period of time. So the red block identifies that once it was replaced, we saw all passing performance, very center line, very minimal drift. And the next black line now is pointing out to the fact that in February 2004, they adjusted the calibration interval, which is represented by, you see a circle here, and the next circle doesn't appear for almost a year. So what we've identified that, okay, we've changed that interval to a year, but yet the drift is still minimal, and we've expanded that out to a 12-month period now with with very minimal decrease in performance for that particular asset. So what I'd like to do now would be give you all a quick demonstration of the CMX software with the history trend analysis, and after that we'll move on to some Q&A, and I'll be happy to address any questions that you have. Okay. So what we're looking at right now is the Beamex CMX calibration management software. And I'll just give you a brief tutorial here on what we're looking at and what the relevance of the information is. If you look on the left side where my pointer is here, this basically gives a listing of all of the assets that you would have in your database. Now, we have two different ways of looking at that. We can look at this by position, meaning we can look at it by, for example, the tag ID, which what we're looking at right now is the very bottom one is highlighted in blue, which is a TT400. I can go up here and click on this one. So what we're looking at here, this is a dryer pressure controller. It's got a location in the plant. It's pharmaceutical plant, plant 1. Finland is block 1, and this is dryer 1. Okay, it actually gives you the location of it and which room that it's actually in. It tells you that the process medium is air, that it's connected by a 1/2-inch MPT connector, and this is the work order number for that particular asset when it was calibrated. There's recommendations for model numbers, Rosemount 3051, for example, and then you get a little more information with regards to where it's owned, and you can place notes for this particular position if that's what you would need to do. Over here to the left, all of these that have dates next to them, starting here with 2712 going all the way back to 219 to 2000. These are all the calibration actions, the history of that particular asset that's been stored in the database since the date that it was put into service. And if we want to flip over to plant structure, as we had discussed a few minutes ago, here where it talks about this in the pharmaceutical plant, plant 1, block 1, it's the dryer 1. If we go to plant structure, we can look at that same asset in terms of where it's located in the plant. So you see this is the pharmaceutical plant, this is plant 1, this is block 1, this is the 101 dryer 1, and this is the asset that we are referring to, and then you see the same record. So there's two different ways to look at that. And what we would typically do is, for example, if you want to see its most recent calibration certificate, what I would do is go to certificates.
Hey there, Eric. It's Katie here. I just wanted to make everyone aware we usually are in the question and answer session at this point. While we are giving this a minute to continue on, I'll go ahead and address a couple of questions that came in here.
Go ahead.
John asked, can we get copies of the slides? Yes, absolutely. I will be emailing everyone a copy of the slides, and there will be a recording of this presentation available as well. It will be posted on YouTube probably within the next week or two. Okay, Eric, it looks like we have another question here for you. Can you repeat the rules of thumb for the increase or decrease calibration frequency based on the past calibration history? And that question is coming in from Richard.
Sure. Excuse me. The rule of thumb would be if you have 3 successive calibration intervals where that particular asset met its calibration tolerance each time, meaning there were no out of tolerance values recorded for any period during those 3 calibration cycles, that would typically justify increasing the calibration interval by 50%. So if we were on a 6-month calibration interval and over an 18-month period, which would be 3 calibration cycles, it met all of its criteria each and every time, then we could increase that calibration interval from 6 months to 9 months. The example that I'm showing you right now is just a standard calibration certificate. And what it shows you is all the information that I talked about earlier, as well as the calibration procedure. And then it gives you a graphical and a numerical view of that particular asset. And as you can see up here, that unit passed. So I'm going to get rid of that, and I'm going to go ahead and run a quick history trend real fast. And that should get us pretty much caught up. Okay, so basically I've opened the history trend window, and at that point I'm going to take this asset, I'm going to drag it over and drop it in here. I'm going to select it, and because I don't want to print it, I'm going to hit preview, and that's going to show me all of the calibration data for that you would see here for each one of these calibration cycles in a one-page format. And it takes a few seconds for it to gather all that information together, but as I stated earlier, it's certainly much faster than doing it by hand. And hopefully I answered the question with regards to the rule of thumb well enough, and if I didn't, then I'll be more than happy to take that a little further here in just a moment. But what you're seeing here is a history trend of that particular tag number. Gives you position, name, all of the information that we saw earlier. The calibration interval is now 365 days. The reject error is the same, it's 0.5% of span. The device ID function, this is a pressure transmitter to a linear device. It gives you the input and output range of how it's calibrated. And what we're looking at here is a graphical representation of each one of those calibration periods for this particular device. And then if we scroll down to the bottom, you can see all of the information in terms of the numerical values of this particular history trend. So you can actually see that the tag ID stayed the same. The asset ID changed, meaning that it was replaced at one point, meaning here in August of 2001, it was replaced with a new asset, and at that time it was out of tolerance and deemed to be out of service. So a new asset was put in, and that asset over time, the average span drift has been very minimal, which kind of justified back down here in 2004, adjusting the interval so that it was now 12 months. So from this particular history trend analysis, we've answered all the same questions that we addressed to the same one in the slideshow. So I appreciate your time, and I'm going to turn this back over to Katie, and if there's any more questions, I'll be happy to answer.
All right. Well, thank you, Eric, for a very informative presentation. We do have a Beamex white paper titled How Often Should Instruments Be Calibrated? That's available for download from our website at www.beamex.com. If anyone would like to view that, I can also email that to you as well. Okay, looks like we have another question from Richard. Richard asks, what about the cal frequency increase rule of thumb for OOT found during calibration? What if 1 out of 3 OOT or 2 out of 3 OOT, out of tolerance, is what OOT is standing for?
Correct. Well, typically, if you are noticing that an instrument is out of tolerance, the last thing that you would want to do would be to expand the calibration interval or make it longer. Typically, if you have an out of tolerance condition, first you would have to determine, is it a minor out of tolerance, is it a major out of tolerance, or is it significant? Minor would be less than 50% of the specified tolerance. Major would be 50 to 100% of specified tolerance, and significant would be greater than 150% of specified tolerance. Typically, if it's a minor, if it's a minor out of tolerance, it would be adjusted and brought back into tolerance through the adjustment process. If it's a major, a lot of times they can be adjusted, sometimes they can't. If it was significant, then that would be a flag to determine, okay, do I need to replace the instrument? Do I need to decrease the calibration cycle? And you would have to kind of look at the data to make that determination. Typically a major would require a major out-of-tolerance condition would require you to reevaluate, say, depending on the calibration cycle, 30 to 50% of the cycle. A significant out-of-tolerance event would typically, you would want to reduce the calibration cycle by half and follow up at that point to see if it was able to maintain its tolerance.
All right, excellent. Richard, hopefully that answered your question. It's been about an hour, so we'll go ahead and conclude the presentation for today. If you all have any questions that come up later on, you can reach us at the Beamex office in the U.S. Our phone number is 800-888-9892. The email is beamex.inc. That's beamex.inc@beamex.com. If you are outside of the U.S., you can email info@beamex.com. That's info@beamex.com. Once again, we'd like to thank you all so much for joining us, and thank you, Eric, for the presentation, and we hope to hear from you soon. Have a great week.